So now that we have a basic understanding of empirical probability, let's take a look at our dice experiment a little bit more in depth. So it says, let's look at a few more specifics about our dice experiment. Below is a frequency table for the dice rolling experiment. So the first column says the total rolls. So I have 1, 10, 60, 150, 500, and 1,000. And then the next column says the number of fives. So if I rolled the die 1, right? I got 0 fives. I rolled the die 10 times and I got 2 fives, 60 rolls, 9 fives, and so forth. So what we want to do is find the relative frequency. So I do this by taking, right, the number of rolls is my denominator and the number of fives is going to be my numerator. So I would take 0 divided by 1, right, which would just give me 0. I would do 2 divided by 10. So 2 divided by 10 would be 0.2. Now I rolled 9, right, out of the 60 of fives. So 9 divided by 60. So 0.15, put a 0 there. And then I have 27 over 150. Which would be 0.18. And then 87 out of 500, which we found that one previously, but we'll do that again. 87 divided by 500, 0.174. And then my last one, right, we've rolled the die quite a bit. 163 divided by 1,000. All right, so 0.16. And so the idea would be continue this experiment, right? Maybe roll the die 5,000 times or 10,000 times and see how many number of fives appear. So this is an actual experiment, right? This is data from the experiment that we did. Now let's just think about for a minute what would be theoretically, which our theoretical probability is sort of in the next section, but just talking about a little bit of an example here. If I think theoretically about rolling a 5, right, on a die, there's 1 5 and there are 6 possibilities. So theoretical probability of rolling a 5, in theory, would be 1/6, or roughly, right, 0.167 would be in theory what we would expect. Now, if I look at the actual data that we did, right, my experiment in my table, you'll notice that the probability of 0.167 really is not very close until you reach 1,000, right? It's getting closer. It's at 1,000, it's 0.163. And so this idea is that the more and more times you roll a die, the closer it gets to this theoretical probability. And we'll talk about that a little bit later, there's actually a theory for this. But let's take a look. It says make a line graph plotting the total number of rolls along the horizontal axis and the relative frequency along the vertical axis. So my vertical axis, horizontal axis. So my vertical axis is going to be relative frequency. And then I have the total number of rolls. And let's see. So my relative frequency, I have 0 to about 0.163, right? So 0, so maybe go by 0.05. 0.05, 0.1, 0.15, 0.2, right? And then for my total number of rolls, maybe go by 200. So I have 0. I have 200, 400, 600, 800, and 1,000. Okay. So now let's go ahead and graph these. So total number of rolls, right? So the relative frequency, right? So I had 1 roll and 0 for the relative frequency, right? So I'd have, it'd be very close, right? Pretty much almost on the axis there. Then I had 10 rolls, right? And my relative frequency was 0.2. So again, very, very close here. So 0.2, a little bit higher. And then let's see. So I had 60 rolls. So I have 60, and then number, let's see, my relative frequency was 0.15. So 0.15, 60, again, it's definitely higher. 150 and 0.18, so a little bit higher. And then 500, so we jump a little bit. 500 had 0.174. And then 1,000, right, 0.163. All right, so if I look, right, what happens is, you know, it's getting closer and closer to this theoretical probability. And if I think about 0.167, right, 0.167 would be, you know, roughly up here. And I know my drawing is, it's approximate, it's not exact. So, but you'll notice that this idea that as we do more experiments, it's going to get closer and closer to this 0.167. It might bounce a little bit above, a little bit below, but it'll start getting closer and closer to that value. And so what happens, and what we call this, it says both the table and the graph illustrate the idea of the law of large numbers, which says as the number of trials n increases, the relative frequency tends towards the actual probability. So let's just do one more example here. It says a group of people were asked if they had run a red light in the last year. 218 responded yes, and 311 responded no. Find the probability that if a person is chosen at random, they have run a red light in the last year. All right, so we have, right, they asked if they ran a red light, and so we have 218, right, responded yes, and 311 responded no. And we want to know the probability, right, that they ran a red light. So the right would be yes. All right, so I'm going to have a numerator, I'm going to have a denominator. My denominator is the total here. So I need to figure out, right, how many people they actually polled. So we would take 218 and add it to 311 to find out how many people they actually surveyed. So 529 people, right? That would be my total, and that would be my denominator here. Now my numerator is going to correspond to those that ran a red light, right? So those are the people that said yes. So those would be my 218. So 218 divided by 529, right? So the probability, right, that the next person, you know, says yes would be 0.4, roughly 12. And so that would be an empirical probability. It's based off of the data that we surveyed the people from.